Hello. In today's video, we will be discussing about the two-body central force problem. Under the classical mechanics, and there are a few terms which are right up there to be discussed first of all. Now, the first term, obviously, we are concerned with two bodies, first up, and then we have a term over here which is known as the central force. Now, what do you mean by the term central force? Now, if we have two objects, a system comprising of just two objects, two masses, and let those masses be m1 and m2, and they obviously are having a certain position with respect to themselves, but most importantly they have there's a coordinate system, of course, and the coordinate system has an origin, and it has the mass m1 supposedly has a position vector r1, and m2 supposedly has a position vector r2 uh, related to them, or with respect to this origin that we have over here. And obviously there are the coordinate, the axis, that is x, y and z axis. Now in these axes, if we were to consider the two body system that we have just mentioned, now in this two body system, obviously you will have a center of mass which will be lying uh, in between the line of the uh, line connecting the two masses, the imaginary line that I have drawn, the dotted line over there. So that will be having a position as well. Now that has a position as well, and that position is supposedly, let me represent it with a capital R. Now this capital R gives me the position vector of the center of mass of that system. Now, as you know, the center of mass, the position of the center of mass is related to the individual position vectors of the masses, as at least for two bodies we have m1 r1, m2 r2 divided by m1 plus m2. This is the value or the expression for the position vector of the center of mass. And from the figure, obviously we can have a relative position of the second mass with respect to the first mass. So if I am to draw this vector over here, let me take it as r vector. So r vector here will be equal to r2 minus r1. How is that? Well, you can use the triangle law for sure. That is, r1 plus r is equal to r2, so r2 minus r1 will give me r. Now, with all that available to us, I hope you know a term which is Lagrangian, that is L, and that is equal to the kinetic energy minus the potential energy term, usually represented as V. Let me take it as U for convenience, because we have been using U as the potential energy in case of electrostatics and um, other chapters that we have dealt with so far. Now, the common notations that we take, I hope you are familiar with them as well. That is, the derivative with respect to time of any coordinate or anything that we take. Let us say this r vector, if I am taking it, dr by dt is simply represented for our convenience as r dot vector. Instead of writing this entire notation as dr by dt, we just represent it as r dot, and that is the way we'll be dealing with in this topic as well. Now, as for the Lagrangian of the system is concerned, the kinetic energy terms will be for both those masses that we have considered, and the relative change in their position vectors with respect to the given origin. So we have half m1 r1 dot squared, that is the kinetic energy for the particle 1. Then we have the kinetic energy for the particle 2, that is half m2 r2 dot squared. R2, remember, is the dot is the rate of change of the position r2, and that is the t term minus the u term stays as it is. U obviously is dependent on r over here, that is its value changes with respect to the position. Now with these things available to us and with this equation that we have over here for r and this equation that we have for the small r vector, which is the relative position between the two masses, we can solve them. You can in fact you can use a rough paper or anything that you are using right now, and you can scribble a few things, and what you will end up with is a new form of relation. What I'm going to give you right now is r1 with respect to this capital R vector is something like this, that is r1 is equal to r minus m2 times of the r vector divided by m1 plus m2. Now this is the value of r1. What about r2? r2 will be equal to r, and in this case it will be plus m1 r divided by m1 plus m2. In case you are unable to get this form, then you can just comment on that. I'll be making a separate video for this short one. So now why did we need this? We needed this to get these r dot terms, r1 dot and r2 dot. Now as evident from this what we have over here we can get is r1 dot will be equal to r dot, that is the derivative of that capital R, minus m2. The rest of the terms obviously are constants, so this is simply r dot divided by m1 plus m2. Similarly, we have r2 dot, and r2 dot is equal to r dot minus, or not minus, plus m1 r dot divided by m1 plus m2. Now these may be looking like completely mathematical approach, but I will make sure that you get the physics of it. Now with r1 and r2 available to us, we can just put that in the Lagrangian. So the Lagrangian, which is the kinetic energy minus the potential energy term, what we get is half m1 multiplied with this entire term, that is r vector dot minus m2 r vector dot m1 plus m2 plus the other term, that is half m2 times of this term, that is r vector, plus m1 r dot divided by m1 plus m2 minus ur. That seems fine. Obviously these are square terms. Now since the capital R terms, they are just r dot, so the capital R terms are just common things. So what we can do is we can just get the L over here, that is L is equal to half. The m1 and the m2 terms are common for this r dot and square of it, and then we have the other term, that is half m1 m2 divided by m1 plus m2, that multiplied with r dot squared. Remember the square because the vector term vanishes with the dot product of the two vectors, and minus ur, obviously that remains. Now if you may think that how did we come across this very short term after the squaring of those two bracketed terms, you can just simplify them, and for one of the minus 2r r dot and the plus 2r r dot, they will cancel out each other, and what you are left with is this. And as far as the m1 and m2 squares are concerned, they will go common. And they will be cancelling out as well. So with this done and dusted, we get back to the physics of it. Now, if you observe this, and when we are concerned about the Lagrangian, and in the Lagrange's equation, now let me just give you a hint of Lagrange's equation. The Lagrange's equation is one of the finest equations that that we have come across, and it helps us to determine the various motion of objects under the principle of least action. And what the Lagrange's equation says is that it is something of this form, that is del by del q dot, derivative of it with respect to time, d by dt of, I'm rewriting it, d by dt of del L by del Q dot. Q is any generalized coordinate, let it be, in this case it is r, it can be theta when you are varying the Lagrangian with respect to the angle, when we are varying the Lagrangian with respect to the angle form, or the position form. In case of position, Q will take the form of r, in case of angle, Q will take the form of theta. So this is the Lagrange's equation. It goes like this, that d by dt of del L by del Q dot minus del L by del Q, that will be equal to 0. Now, as you can see over here, what we get is, in case of the Lagrangian, when we are concerned about the if we are concerned about the r vector coordinate, well, in case of the r vector, if we divide this instead of q, what we get is, if we take this capital R, right, and in that case it will come to 0 completely, and the Lagrangian in that case will be 0, and that being equal to 0, those kind of coordinates are simply termed as cyclic ones. These are the cyclic coordinates. Now, they do not really make any sort of impact, and so r being the position of the center of mass, what we can make out from this observation is that the center of mass, either the center of mass remains constant, or the center of mass moves with the velocity of the center of mass remains constant. So it is moving either with a constant velocity, or it is completely at rest. However, the objects, if it is at rest, however, the objects m1 and m2 that we have considered right at the top in the diagram, they keep on moving, and the only way that they move and the center of mass remains at rest is the circular or the orbiting motion about the center of mass. So this kind of keeps us gives us the notion that how the two body or the two object system carries about its motion. Most of the times, in cases with these masses involved, the two bodies, they move about the center of mass, where the center of mass remains at rest. It must remain at rest, because that is how we are getting the equations which are supporting our explanation. Now, there is one more term that you might have a look at, want to have a look at, is this term. This thing that you are observing is, if you know, is the reduced mass. And because we are not really getting any kind of help with this r coordinate over here, we can just do away with that. That is not at all necessary to write that. So the Lagrangian is now just concerned with half mu times of r dot squared minus ur. Now, this mu times of r dot squared, this mu is what we term as the reduced mass. Now, reduced mass is the consideration where we take the two particle system to be a single one particle system. Now, the assumption here is that, let me take you to the next page for that. We wish to make things easier for us. So instead of those two body complicated stuff, what we do is we just reduce it to a single body problem, where the single body is the reduced is having the mass of the reduced mass mu, and that has a position r vector which is moving with respect to a fixed origin. Obviously there is the x, y and z axis. Now this is somewhat the motion is all about, but if we move back to the original diagram, what we see is that there is a center of mass over here, and the center of mass, from that center of mass, now we converge the origin to the center of mass supposedly, then we have this mass m1 which is lying at a distance say r1 from that center of mass, and this is lying at a distance r2 from the center of mass, this is m2. Now m1 goes about supposedly a circular motion about the center of mass, and this m2 also performs a similar circular motion about that center of mass. So this is how we can describe the motion of the two bodies that are associated um, in that system. Now this is much easier approach, which is the case of this diagram rather than that. But if you might have guessed it, that we had earlier given the distance between those two masses m1 and m2 as r, and here the distance that we have taken of the reduced mass with respect to origin, that is the position vector of the reduced mass with respect to origin, that is also the r vector, which means that the two bodies, out of those two bodies, we can consider one of the bodies to be here at the origin and the other body to be over here, and that body, this reduced mass, the body having the reduced mass, that orbits about this body, which makes it an inertial case for this mass over here. However, for this mass over here, it is attached to a non-inertial frame. Now we can, however, get a picture of how these things are turning out to be by considering the masses, the magnitude of the masses. Now consider the case where we have the reduced mass, we have the expression for reduced mass for sure. Consider the case where m1 is much greater than m2. Now if m1 is much greater than m2, what happens is that for mu, which is equal to m1 times of m2 divided by m1 plus m2, what we get is this m1 that can go down over there and get divided. So we are left with m2 over here, and m1 divided by m1 plus m2 divided by m1. Well, this thing cancels out, and what remains is that m2 divided by 1 plus m2 by m1. Now 1 plus m2 by m1, this cancels out to 1 for sure, but this won't cancel out, and this just reduces to nearly zero value because m2 is very less as compared to m1, and that is why what you are left with is m2 divided by 1, which is simply nearly equal to m2. Now with this nearly equal m2 value, that means we are just concerned this mu has changed to m2, which means that over here in this first diagram that we see, instead of mu we write the mass as m2, we keep the mass m1 over here, m1 stays there, m2 orbits about it. This is mostly the case with the sun and the planet system, and also in case of the nucleus and the electron, even in case of the hydrogen atom, where you have one electron and one proton in case of the positronium, where you have the single proton inside the nucleus and the electron revolving around it. The electron is actually the mass of the electron is if you know it, is 1 by 1836 the mass of the proton. That is why which obviously means that mass of the electron is much less than the mass of the proton. So the electron in this case, considering the masses, the electron M2, with that M2 expression over here, that revolves around the nucleus containing the proton in that case. So that more or less helps us to understand what kind of motion is carried about by a two-body system, where we are considering the center of mass frame, as well as we are considering the comparison. We are comparing the masses of the two bodies. So this is the case of motion. Now, if we are to consider how they move exactly, now obviously they are moving in a circular path, or maybe in an elliptical path, as described by further experiments for higher atomic number for higher atomic numbers. Now, the central force that we were concerned with, right, in the beginning, the central force problems that we are concerned with, as obviously that we can see from these figures that we have over here, what we know is that the force will be somewhat like a centripetal force. And with this in picture, with this diagram to be taken into consideration, what we get is that a particle of mass mu, that is the reduced mass, is moving about a fixed massive object, and it is moving perhaps in a circular path, and the velocity is a fixed one. This is the angular velocity that we have considered, omega squared, and that multiplies with r, and this contributes to the centripetal force that we have studied so far. Now, the centripetal force, the expression for the centripetal force obviously gives us an idea that this force that we are concerned with, the central force, that is, the central force takes the form of some function of r, and it is also directed along the direction of r. So what we get is, we can just rewrite it as r vector divided by the modulus of r, or the magnitude of r. That is for the r hat unit vector. Now, with this r vector or r cap that has been provided, what we get to know is that if in case the force is attractive, it will be directed towards the center for sure. And in that case, the r vector, which gives me the position of the reduced mass, that is directed outwardly. So in case of attractive forces, the expression of F, that goes to negative, or we can say that Fr becomes negative. And for repulsive forces, obviously they will be directed along this position vector. So for those repulsive kind of forces, Fr will have a value which is greater than 0 for sure. Now, as it depends on the position, this force, this central force, as it depends on the position, it is path independent, and therefore this Fr that we have is a conservative force. It is always a conservative force. Now with the conservative kind of forces, what we have is that they are just related to the potential energy term, that is U, as the partial derivative, the negative of the partial derivative of the potential energy with respect to the position. So we have F, that we had denoted F to be equal to minus of del U by del R cap or R hat. Now with the, as far as the rotation or the motion along the circular path is concerned, with the orbiting motion, what we get is that the angle won't make any impact, because the angular velocity remains constant in this case. So the angle doesn't really make any form of contribution to the it does not make any changes, so that also becomes the cyclic coordinate. So that can be discarded as far as the Lagrangian is concerned, and thus we have a constant angular momentum, where the angular momentum here is represented by J. Mostly we represent the angular momentum with L, but just to keep it away from the Lagrangian, which has the same kind of notation, so we just keep it as J, which is equal to R cross P, P being here the linear momentum, and this J term that we have, the angular momentum, that remains constant in this case. In the absence of external force, obviously there is no as far as the first law of motion is concerned, with the absence of external force, obviously the angular momentum must remain constant. Now if we can just write this as taking the dot product of J and R. If we take the dot product of J and R, I write it like this for convenience. Then we have R dot R cross P, and as you know that dot and cross can be interchanged, so we have R cross R dot P, and R cross R obviously goes to 0, so this value goes to 0, and because this value goes to 0, what we get is R dot J is going to 0. That means they must be perpendicular to one another. Now with R being the position vector, that is always perpendicular to the angular momentum, and so this gives us an idea that this motion under the central force, it is always restricted to a certain plane. It cannot be taking different planes. What it means is that for a kind of motion that we are considering right now, these kind of central force motion, they are restricted to a certain plane uh, in the instantaneous position given the instantaneous position of the particle and the polar coordinate. Now having come this far, we can now dare to move along with some equations of motion that we can deal with under the central force. So what we are going to discuss now are the equations of motion under the central force. Now, given the nature of the force that uh, we have just mentioned above, FR hat, that is obviously a conservative one, so del U by del R hat. Now if we consider this origin with respect to which a particle is moving, and here we have the vector as the R vector, the position at the point P, and it's moving along this line, and it goes to a certain point over here, let it be P dash, and the position over there is something else, of course. D theta is the angle swept in this case, and let me drop a perpendicular from the point P onto the position vector of the point P dash. Now obviously from the diagram that we have over here, for d theta being a very small infinitesimal distance, what we get over here is that this value of this line that we have over here is simply r multiplied with d theta. The arc length is almost a straight line, and with that available to us, let's see how we can obtain the equation. Now in order to obtain the equation, obviously we take the help of the Lagrangian. Now the Lagrangian in this case, t minus v is equal to half, and we have m r dot squared for the linear case, and as far as the angular case is concerned, with the constant angular velocity omega, remember omega is d theta by dt, that is the rate of change of angular displacement. We can, however, denote it with theta dot, the shorthand notation that we are using, that I had mentioned previously. So mr dot squared is instead of mv squared, and mr square omega square, that is for the angular speed, we can write it as mr square. Instead of omega square, we are writing as theta dot squared, and that is the kinetic term minus the potential term, that is ur. Now del L by del theta, as we had mentioned, is going to be 0, so that is why we had taken it to be a cyclic coordinate that I have just mentioned above. So that is not to be considered, and however the canonical momentum, that is p theta, that is the angular momentum, of course, is del L by del theta dot, and this is the canonical expression for it, and that is equal to mr squared theta dot, and this is the, of course, the angular momentum that we had just discussed earlier. Now coming back to the Lagrangian equation, d by dt del L by del theta dot, we are concerned with the theta coordinate. Now we'll be dealing with the r coordinate as well. So del L by del theta dot minus del L by del theta, obviously that goes to 0, we have just, and this is equal to 0, this goes to 0 as we know it, and so what we have is, this implies a d by dt. Well, del L by del theta, as we had just mentioned, is mr squared theta dot, mr squared theta dot, and that is equal to 0, which gives us that mr squared theta dot, which is obviously equal to j, is a constant that we have mentioned above. So j is constant. Now one of the first integrals of motion is what we have just obtained. Now with this thing available to us, what we can proceed further with is that let me take the derivative with respect to time of a term r square theta dot, that is this term, and for our convenience let me just add or multiply a term half. Makes no difference, because r square theta dot derivative of it goes to 0. The half derivative of half, that is also constant, that can also go to 0. That is quite okay. And so this term that we have, half r square and theta dot, let me take it as some constant term, let us say k, small k. We will be using the k later, not this k, but we'll be using that in capital letters. Now keep this in mind and just move over to the diagram that we have done over here. Well, the area that has been swept while it goes through an angle d theta from the point P to the point P dash, the area OPP dash that we see over there, that is a small area dA. Well, we are just concerned with that triangular area that we see, and for that triangular area the value of that area is half of the base being equal to r in that case, multiplied with the altitude. Altitude, as you can see, is that arc length that we had just discussed, that is r times of d theta, and this is simply equal to half of r square d theta. And take the derivative with respect to time. I just write it like that. So what we get is half of r square theta dot, which is this one, and that's a constant value, as you know it. We have checked it over here, it is constant. And with that being constant, that tells us that the aerial velocity of an object which is moving along this which is orbiting or under the influence of the central force, the aerial velocity has to be constant. And remember, this is the Kepler's second law in case of the planetary motions, which tells us that this term over here, that is a constant. Now if we consider the Lagrangian for the r coordinate now, so what we get is we take the next page for it. D by dt, the Lagrange's equation, del L by del r dot with respect to the position vector, del L by del r, that goes to 0 as far as Lagrange's equation is concerned, and del L by del r dot, as you can see in that Lagrangian that we had just written in the previous page over here, for this expression that we have over here for the Lagrangian, that is L t minus v half m r dot squared, and taking the derivative with respect to r dot, what we get is simply mr dot. We are going to end up with that. That remains in bracket d by dt. Oh, written it in another page. So that is d by dt m r dot, right? And moving back again, in this case over here, what we get is the second term, that is that has an r, so del L by del r, which is the next term in the minus case, well, that remains as mr theta dot squared. So we have the minus mr theta dot squared, and obviously the term which was for the potential term, well, that was in negative. Now minus of minus becomes plus, so del u by del r, and that equates to 0. And then, as del u by del r, as you know, is simply f of r, minus of del u by del r is f of r, because that is in plus now, so we can write it as a minus of f of r, and we can take it over to the other side. So what we get, this derivative with respect to time again, well, this is mr double dot, then double derivative, and minus mr theta dot squared, and this is because this is minus of fr, the minus of fr can go to the other side and become plus. Now if you remember that j is equal to mr square theta dot, so instead of theta dot what we have is j divided by mr square. So we can just put it over there because we want it to be completely in the dependent on the position. So mr double dot minus mr j divided by mr squared whole squared, because that is a square term, that is fr, and so we get mr double dot, and one of the m's get cancelled and one of the r can get cancelled, so we are left with j square divided by mr cube, and that is equal to fr. This is the second order differential equation in the r coordinate, and because this is a negative term as well, what we can do is we can just take it to the other side and use the derivative with respect to r in this case. So what we do is we keep the mr double dot over here and we take the j square onto the other side, where it won't be wrong if I write this one as simply as minus of half del by del r j square by mr square and plus u. The half, well, the half is outside. I can wait. I first write it as like this, and then plus del u by del r stays as it is, and then what I do is, of course this is minus, and mr double dot, and we have the minus can be taken out, so minus del by del r half of j square divided by mr squared, and this is now plus u. Well, if you are confused with this thing that I did over here, let me just give you a hint of that. Del by del r of j square by mr square, if I am to do that, then what I do is, obviously I have put a minus half over there, so what this operation does is that del by del r, because it is r squared, so this is minus 2 j square by m, obviously they are constant, so they are constant terms. Now as far as r to the power minus 2 is concerned, minus 2 r to the power, so this goes as 1 by r cube, and that is exactly what we would have obtained. The minuses would have cancelled out, and what we would have obtained is j square divided by mr cube, which is exactly the case if this term would have gone on to the other side. And that is what we did, and we just simplified it like this. So with this simplification done and dusted, we would try a few more of those things. What we can do is that we just multiply an r dot over this side, and why should we leave this side as well? We multiply this side with r dot as well, so what we get is j square by 2mr square and plus u, and that multiplied with r dot as well. Now with this we can write this as this is nothing, if you observe it, this is nothing but the derivative of half mr dot squared with respect to time, because you do this derivative and you reach over here. And as far as the right hand side is concerned, what we get is del by del r. I'll take it one step at a time, and because this is r dot, well, r dot is simply dr by dt, isn't it? Well, dr by dt, this would have been the case if I take the entire derivative, the derivative of the entire term, and keep it like that. That is j square divided by mr square 2mr square plus u taken over the entire the derivative taken over this entire system, and this would have led to this, and simplified as this, and we would have, this is just the way of doing the reverse derivative terms, and that is why these are known as first integrals. So if we integrate both those sides, now that we have them, dt can be taken care of. So integrating both these sides, well, I have to rewrite it again? Well, I just did it. So dt is well, strike that out. So integrating both these sides, what we get is those same values, that is half mr dot squared is equal to uh, minus of this term, that is j squared plus 2mr squared plus u plus some constant. And hang on, what's that constant? That constant, I name it as the total energy. So half mr dot squared plus j square divided by 2mr square plus u, which is the potential energy term. This is the kinetic energy, this is the potential energy, which gives me the total energy, and that obviously remains constant. And conservation of energy is verified, so this is completely and wholly true, and this obviously gives us an idea of the equation of motion of the particle having. Now this obviously the m that we have used over here is the reduced mass that we can consider, because as we have seen that m2 was the reduced mass in case of the massive and the lighter particle system, such as the planet and the sun, the nucleus and the electron. So here this m represents the mass of the electron or the mass of that planet, which is exactly equal to, which is nearly equal to the reduced mass, or taken in place of the reduced mass. So these are the equations, and these are the first integral terms that we obtained, this one being one of those first integrals, and the other one that we had obtained is for the uh, this integral term over here in the previous page over here, that is mr square theta dot is equal to j, and that was constant. So these are the equations that are associated with the body or the motion in under the central force. We'll be moving further in the upcoming videos related to the orbital motion, how we are getting the notion of the orbital motion, and what kind of properties do these orbital motions exhibit, but that will be dealt in the videos that are up next in this series. Till then, thank you for watching.